So in this video, we're going to talk about light, which allows us to navigate the world, and it also allows us to navigate atoms. So first, we're going to talk about some properties of light. We can measure the wavelength, okay, which is the distance between identical points on adjacent waves. And we can measure the frequency, which is how many cycles it goes through in a second. And we know that all light travels at the speed of light. So how fast is that? It's about 186,000 miles every second. In chemistry, we're going to describe things in meters per second. So that's 300 million meters per second. And basically, we have a whole bunch of different types of electromagnetic waves. We have ones with really long wavelengths, like radio waves, all the way through microwaves, infrared being a little bit shorter than that, visible, ranging from 700 nanometers in length if we're talking about red light, or 400 nanometers in length if we're talking about blue light. So a very, very small region of the electromagnetic spectrum is actually visible to our eyes. The rest of it we can't see, but it still has the same properties, just slightly different wavelengths. Then, once we get past the visible region, we start to get some higher energy or ionizing radiation like ultraviolet light. Then X-rays even shorter than that, and then gamma rays even shorter than that. So we go from low energy radio waves to high energy gamma rays, and there's everything in between. Okay, so talking about the three properties of light today, of energy, wavelength, and frequency, we're going to describe those relationships graphically, and then we're going to do some calculations with them. So first, if we compare the energy and the frequency, if a wave is traveling across the room at the same speed of another wave, but it's going up and down more, it's going to be carrying more energy. So we say that's a direct relationship. And if we plotted the energy of a photon versus its frequency, the slope of that line is going to be Planck's constant, which is a really, really small number, but it relates how much energy a photon of light has for every cycle it goes through per second. Okay? Then, if we're comparing the other properties, so if something is going up and down a lot, it's going to have a very short wavelength. If it's going up and down a little bit less, it's going to have a longer wavelength. So the relationship between energy and wavelength is going to be inverse. Long waves have less energy. So if we plotted that, it would be like you were plotting y equals 1 over x, inverse relationship. And if we generate an equation for that, the y, energy, is going to be equal to something over that x. And that something is going to be equal to Planck's constant, which we just put right here, very, very small number, times the speed of light, which is a relatively large number. But when you divide the product of those by the wavelength, you'll get the energy for that photon. And lastly, the relationship between wavelength and frequency is going to be inverse as well, and that's related by the speed of light. So most of the time you'll see it written like this, where the speed of light is equal to the wavelength, so how long the wave is, times how many cycles it goes through per second, which is our frequency. And up here you can see a few calculations we did comparing light from the different regions of the spectrum. If we have radio waves, we picked the station KISS 108, which has a frequency of 108 megahertz, which gives us a frequency of 1.08 times 10 to the 8 cycles per second, or 1 over s. We can relate that to the wavelength using the equation we just learned. The speed of light divided by the frequency is going to be equal to the wavelength. So we plug in those values, and we'd see that the wavelength of KISS 108's photons they're emitting from the radio station is 2.78 meters. And that would have an energy using this equation right here, the frequency times Planck's constant, we would get a value of 7.16 times 10 to the negative 26 joules. Again, these are photons, so none of them are going to have a ton of energy, but this is even low on that spectrum. Comparing that to red visible light, which has a wavelength of 700 nanometers, or 7.00 times 10 to the negative 7th meters, you could calculate the frequency by using the speed of light equation. We could do that. And we can also calculate the energy using this equation right here. Plugging in our values for Planck's constant, speed of light, and dividing that by the wavelength, we'd see that this has an energy of 2.84 times 10 to the negative 19th joules per photon, which is, comparing these two things, 10 to the 7th times more energy per photon. So we're talking 10 million times more energy per photon when you're comparing visible to radio light. Then we did it for gamma rays. So gamma rays can be about 10 to the negative 12 meters long. okay, which is really, really, really small, really, really short, and those carry a ton of energy. And using those same equations, we see that the energy given off by a gamma wave or gamma photon is gonna be on the order of tens of trillions times more energy than that of a radio wave. And that's why gamma rays, which are given off by things like nuclear events, are so damaging. And same thing with X-rays and even some UV light. These lead to harmful effects when they hit us because they can break bonds within molecules, including our DNA, which is really not good and lead to mutations and further health problems. Anyway, this is the electromagnetic spectrum and how we can relate the different properties of light.